So, good morning everyone. In this lecture, we will be covering F block elements in one single lecture for your JEE Mains or the NEET. And I have only used NCERT as my source. One second, my throat. I have only used NCERT as my source and I have tried to include as much information as possible. You know, NCERT has those paragraphs in which lot of information is given. So what I did, I just attached a screenshot of those paragraphs. Like this paragraph had a lot of information, so I just added it. So because I did not want to write all this, and so you can just check the text for yourself. And the other text of NCRT from which I could extract points, I have done that, and I am sure I haven't skipped a single point. But if I have, feel free to let me know. And this is going to be enough for your JEE Mains. If you haven't seen though, it is preferable if you watch the D block element once before this, but that's all. And I would like to talk to you about one thing. I'm recording and posting this in early morning, like it's like 12 p.m. here. Usually I post at 6 p.m. The reason is that I have been invited to a relative's place because of some unexpected situation, and unfortunately, I will not be able to cover POC and biomolecules before 28th of January. And in the evening, we are going to leave. So, in the morning, I'm recording this for you. So, at least I can say that I have finished block chemistry. And if you want to do biomolecules, a video will come later. But for now, before your mains, you can check out Math on Go, or if you want to do POC, you can check out Simply Concise. Now, let's start learning about the F block elements. And basically, we studied P block, S block is deleted. Now, the F block elements, this is the Lanthanoid series, basically the 4F subshell with variable occupancy in the 4F shell, and this is variable occupancy in the 5F shell. Now I am not going to give you a trick to remember these elements because I want you to brute force them into your memory along with the atomic number. Like you need to know that cerium is 58, praseodymium is 59, neodymium is 60, promethium is 61. And why is that? Because you need to know both the full names of the the elements. You need to know the atomic symbol. You need to know the atomic number. An easy way to try and remember this is instead of thinking of this like a row, like an Excel sheet, think of them like neighbors. Like praseodymium has cerium behind it and neodymium ahead of it. Similarly, these triplets will help you remember the order of the elements, and especially you need to know the Lanthanoid series. Actinoid is not that important, but still preferable if you have learned it. Okay. So that was it. Let's learn about the general points. Well, lanthanum is not a part of the lanthanoids. This lanthanum is not a part of the lanthanoids. Like you see, lanthanum belongs to the mainland of the periodic table. It's 57, and after that we skip to 58. The 4F subshell gets filled. Then we come back to 72. 4F has like capacity for 14 electrons, so you can say the difference is 15 here, but you know the numbering will cause there to be 14 elements between this. Okay, so from hafnium to your mercury, then to actinium, say you begin actinoids, lanthanum, say you begin lanthanoids. So actinium again, there is a skip of 14 elements. Then we go to rutherfordium. Okay. So let's take a look at the names of these elements. This is cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium. I forgot what this was. Thulium, ytterbium, and lutetium. Okay. So lanthanum is not a part of the lanthanides, but studied closely with them, just like zinc, cadmium, and mercury with the D block elements. And the same happens with actinium and the actinoids. Now let's learn about the general properties of lanthanoids. All lanthanoid show positive 3 as the only stable oxidation state, and as a result, sometimes we say that all of them belong to the third group of the periodic table. Okay, like they have a common oxidation state plus 3, and even if they show other oxidation states, they eventually come back to the third state. Okay, now the atomic and ionic radii, let's look at that. Your plus 3 ion, like we know they show plus 3 oxidation state. So if we learn about the ionic radii of their most stable oxidation states, it shows a beautiful and constant decrease, which is very smooth. You can say this is a very smooth order, and it pleases my eyes for there to be no exception in a concept of inorganic chemistry. How long have I waited for something like this? So beautiful, it's just immense, it's immaculate, and it's beautiful. You cannot change my mind. Well, your metals like base metal and also show a fair trend. They show a very decent trend. You can see it decreases, except for your europium, which jumps up to even larger than lanthanum thanks to its stable configuration of F7. Okay, so that was it for the radii. In very small, if I explain you what lanthanoid contraction is, lanthanoid contraction is basically, you know, the 4F shell and even the 5F, but let's learn about 4F right now. It is terrible, like absolutely shit at shielding. It cannot shield outer electrons, and as you add, like imagine this is the F subshell, as you add more electrons, of course this nucleus also gets more positive charge, but the shielding is so terrible that it is not able to protect the outer shell from the Z effective of the nuclear charge. So the positive charge increases, but the negative charge is not shielding each other. So this just gets pulled back in. And this explains the regular decrease in the in the base metal ion and the M3 plus. And this is what we call the lanthanoid contraction. Now, as a consequence of this, the radius of a 3D element, like the radius of a 4D element, this is the transition series. I'll explain it on the periodic table. This is the 4D transition series, and this is the 5D transition series. Now notice one thing, that in the 5D transition series there is a small gap, and this gap is what is gives birth to the lanthanoids. And since of this lanthanoid contraction, the radius of the elements gets smaller and smaller, and which is why you can say that the radius of zirconium is 160 picometers, but the radius of hafnium is 159 picometers, which is why they exist and even occur together. They have very similar chemical properties as well. Okay, and in D block we studied, which is why the radius of the 4D series and the 5D series are very close to each other. Remember, there is an exception to this exception, which is the scandium, yttrium, and lanthanum, because lanthanum has no F subshell, so it does not show lanthanoid contraction, and the radius increases as normally expected. So that was it about lanthanoid contraction, and it is going to be the leading cause of a lot of properties of the lanthanoids. Okay. Now let's learn about the oxidation states of the lanthanoids. I have attached the NCERT. Let's read it together. The lanthanoids oxidation states. Your basically Ln, it is not natural log. Ln is not a chemical symbol, element symbol. It is basically a general lanthanoid. Like this comprises of gadolinium, europium, terbium, whatever. All of them is represented by Ln. Like somehow we use M for metal, so we use Ln for lanthanoid. Now, in the lanthanoids, as we know, this is not a part of the lanthanoids. Hence, they are written separately here. And lanthanum plus 3 and lanthanoid plus 3 are predominant. Like we know, plus 3 is the dominant oxidation state. But sometimes they are saying that plus 2 and plus 4 have also been observed. Now, this irregularity is because of extra stability of empty and half-filled F subshell, which means that formation of cerium 4 plus. Like cerium 4 plus, if we remove 4 electrons from cesium, whose atomic number is 58, it goes down to 54, which is the atomic number of xenon, which means it gets noble gas configuration. But even even though it has noble gas configuration, it has gotten very good stability. It has noble gas configuration. Still, it is an oxidizing agent, which means it still has tendency to go back to its third oxidation state. And it's not like this reaction is very cerium is confused. No, cerium is not confused. Cerium is determined with 1.74 volts. For comparison, the Daniel cell in electrochemistry has an E naught of 1.1 volts. This reaction is even more spontaneous than that. Like, it is obvious for cerium to go with its third oxidation state instead of the noble gas configuration. And its E naught is so high, it suggests that it can oxidize water. Just think. Think what this means. Bro had everything and he gave it away just to be in its third oxidation state, and hence cerium 4 plus is a strong oxidizing agent. And this was a direct question in a JEE Main PYQ of 2025. But there is one thing. This reaction, oh, I've written Cu. One second, let me fix that. It's not copper. Give me a second. It's cerium, which is Ce. Okay. Now, this reaction where it is converting from Ce4 to Ce3, this is a very spontaneous reaction, but if we look at its kinetics, this reaction is very slow, which is why it also allows us to analyze this reaction. Like, it's a good analytical reagent. Like, it's oxidizing water. Okay, it is oxidizing water, but this reaction is slow. So if we want to observe the reaction where water is getting oxidized, then cerium is a good reagent for that. Now, let's move ahead. Now, praseodymium, neodymium, no, wait, this was promethium, sorry. Promethium, neodymium, terbium, and dysprosium, they also exhibit +4 state, but only in oxides. You know, oxygen has an ability of stabilizing the higher oxidation states we studied in D block elements, and similar can be seen here. So, mnemonic is, do you not pray for 3? Which means that are you fine with what you have? Do you not want the third oxidation state? Do you not want to pray for 3? So how do you used to remember? Using D and U, remember dy or dysprosium. Using N, remember neodymium or Nd. Using Pr, remember promethium or Pr. And using the T of 3, you remember terbium. Okay. Do you not pray for 3? Which means that these elements are fine with having a oxygen atom attached to them while they are in the +4 state. And oxygen, I guess you can remember by this, and this. But that's it. That was the mnemonic. Let's move ahead. See, your europium 2 plus has an F7 configuration. Okay. Which is, F orbital has 14 electrons, and if it has a F7 configuration, this is half filled and this is very stable. And EU2 plus is still a strong reducing agent. Are you kidding me? If it is a strong reducing agent, this means that from it wants to get oxidized itself. From EU2 plus, it wants to become EU3 plus, which means it likes its third oxidation state more than its half-filled configuration. What blasphemy is this? This goes against anything that I have ever studied in chemistry. But, my friend, this is why I have attached this meme. Lanthanoid looking at +3 oxidation state. Look in those eyes. That deviousness in its eyes. He's a monster when he looks at the +3 state. And let me tell you, there are absolutely no exceptions to this. Like, even you think half-filled wasn't enough? Look at ytterbium 2 plus. It has F14 configuration. Its F subshell, it is fully filled. And even in its fully filled state, it is still a reductant. It still wants to grow from +2 to +3. Man, I cannot comprehend this. What blasphemy is this? EU2 plus and ytterbium 2 plus gave up their filled shell for M3 plus configuration. That's how much they love the plus 3 state. Understand? Okay. Terbium 4 has half-filled f orbitals and still acts as an oxidant, which means from its fourth state it wants to get in the third state. Again, violation of the half-filled thing. And behavior of samarium is very much like europium, exhibiting both plus 2 and plus 3 oxidation states. Now, NCERT doesn't mention this, but obviously the plus 3 will be more stable. Okay, so that was it. Note it down. And let's move on to electronic configuration. Now, a while ago, I got a comment telling me that they have a lot of trouble remembering the electronic configurations of the F block elements. And I am here to make it easier for you. But this time, I am not going to tell you a trick to memorize this. I will tell you the entire concept of how to write the electronic configuration. Okay. Now, one thing I want you to do is remember all of these elements with their atomic numbers. It is necessary. It is necessary, absolutely necessary. Like if you want to do F block elements properly, there is no escaping this. You need to learn these three columns by brute force. And I'm not telling a trick because I want you to remember every single thing down to the full names. Okay? Now, let's learn the electronic configurations. I'm not going to be like, kids, remember, lanthanum is 5D16S2. Kids, remember, praseodymium is 4F36S2. Hell no, I'm not doing that. Let's look at basically what is electronic configuration. It is the configuration of electrons. Like, yeah, no shit, but this is the entire order from 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. This is the configuration of xenon, a noble gas. And after xenon, actually no, this is not configuration of xenon. Until this point, this is the configuration of xenon. But as you can see, the 6s2 shows no exception here. It is always 6s2. So I included that in here itself. This will show no difference. The general configuration of any F block element in the Lanthanoid series is going to be these 56 electrons with some electrons in the 5d subshell and some more electrons in the 4f subshell. Now, look at this genius. Say you have erbium 68. Its atomic number is 68 and we know that it is going to definitely have these 56 electrons. So we remove them from 68. Why? Because if we minus 56 from 68, we get 12, which means that there are going to be 12 electrons in its 5d shell and 4f shell combined. And a good thing is that except for lanthanum, cerium, and lanthanum is not even a F block element, except for your cerium, gadolinium, and ytterbium. No, not ytterbium, sorry, lutetium. Except for those lutetium, gadolinium, and cerium, none of them have an electron in their 5d subshell. And even the ones that do, they only have one electron. Which means all you have to do is if you have to write the electron configuration of any of these elements, you have to note its atomic number, remove 56 from it, and whatever's left, if it is 58, 64, or 71, give one of those electrons to the d subshell and the rest of them go in the 4f subshell. That's it. And I have made a small mistake in the notes here. This is basically I have given a solved example. This is not 70, this is going to be 71. Like I was high when I was writing this paper. You can tell by the handwriting. And this is not 70, this is 71. It's basically a written explanation of the effect for those who are not watching my lectures directly and instead using my notes. Okay. So this is it. This was how you could tell the electron configuration of any of the F block elements. And for lanthanum, you can remember separately. It has no 4f electron, only 5d1 and 6s2. And let's understand why this exception happens, where instead of going in the d subshell, the electron just jumps into the 4f subshell all of a sudden instead of going into like d2, d3. Well, understand one thing. The 5D and 4F subshells have very, very close energy. Like, absolutely close energy, almost identical. So, using Pauli's exclusion principle, using Hund's rule of maximum multiplicity, if these orbitals are degenerate, before electron pairing can occur, they go into the 4F subshell. Okay. Now, they have very close energy. After this electron comes, this alters the energy of the 4f and 5d subshell, and then coming electrons are just added into the following, like this. And the your third oxidation state, it shows a smooth trend from 0, 1, 2, 3 all the way up to 14. Okay, and this exception happens because gadolinium achieves a stable half-filled configuration by removing one of the electrons from its F shell to move to the D shell. Only for cerium, gadolinium, and I am so high. Only for cerium, gadolinium, and lutetium, this exception is shown. Oh, that's so ugly. 1 second. Only for cerium, gadolinium, and lutetium, this exception is shown. Understood? These were solved examples. Download the notes and look at them. Here we have, like, I have given myself a question. Write electronic configuration for your dysprosium, europium, and gadolinium. So you write down the atomic numbers, subtract 56, get the answer. This will be the sum of your 5d and 4f electrons. Now write down the two possibilities. If this has 10 electrons, now either all of them go to the F subshell, or either one of them goes to D subshell and the rest go to F subshell. Now, is its atomic number in this list? If not, choose the one which has no D subshells, no D electrons. Again, if 63 europium is not present in this list, 58, 64 and 71, I'll change it. Choose the one with 4f electrons and no 5d electrons. Now gadolinium, 64 belongs in this list. So instead of the one where all of them go in the 4f subshell, you choose the one in which one of them goes in the D subshell and the other go in the 4f subshell. Okay, understood? I'll fix this. Give me a second. That's so ugly. Array. Yeah. So this was it about the electronic configuration. Let's learn about the physical properties of lanthanoids. Now all of them are silvery white soft metals. What does this mean? They are silver-like their appearance is close to that of silver, and voila, they also tarnish like silver. So use this as a link to remember. Go, shall drink some water. Give me a second. Yeah, so hello again. Let's continue. So, your they tarnish rapidly in air and they're very hard. Like their hardness increases with atomic number, and the samarium Sm is very hard. Like it is being steel hard. Like it is as hard as steel. Their melting points are between 1000 Kelvin to 1200 Kelvin, but samarium melts at 1623 Kelvin. Again, you can use this as a link. This what does this imply? It means samarium has a very strong lattice, which is why its melting point is very large than the other lanthanoids, and also it has very hard. I mean, it is very hard. Like materialistically, it is hard. So it is steel hard and has a high melting point. Connect those facts. They have typical metallic structure and they are good conductors of heat and electricity, which means they are basically just typical metals. Okay. Now, the trivalent lanthanoid ions. They are colored, which means they show color both in the solid state and in the aqueous solution, except for your lanthanum 3 plus or lutetium 3 plus. Why? Because they have the F0 configuration or the F14 configuration, fully filled or zero filled configuration. And but the rest of them show colors. Okay. The lanthanoid ions, other than the ones which have zero configuration and the ones which have full configuration, they are all paramagnetic. Which means again, if there is full configuration, there is electron pairing at every orbital possible, and if there is zero configuration, there are no electrons, and everything is paired in the inner orbital, so there is no paramagnetism observed. But here they're paramagnetic, which ones? Which don't have these configurations. And this paramagnetism, it is maximum in neodymium, which has the most unpaired electrons. Now, their first ionization enthalpy is around 600 kilojoules per mole, and their second is about 1200 kilojoules per mole, which is analogous to that of calcium. Okay, I have written the points here. Let's look at their chemical properties. Now, the earlier members of the lanthanoids, they resemble calcium in their chemical reactions, but the later ones start resembling aluminium. Okay. Now, this reaction, you know their plus 3 state is the most stable state, and if you want to turn the lanthanoid plus 3 ion into its base solid metal, this reaction is non-spontaneous and its E naught lies between minus 2.4 to minus 2.2. A negative E naught means that this reaction is not spontaneous as the Gibbs energy comes greater than 0. Gibbs energy is given as minus NF E naught. If this is negative, then this whole term will become positive, and Gibbs energy when positive means the reaction is non-spontaneous. Now all of the lanthanoids have their E naught for this reaction, this particular reaction, in between these values, except for minus 2.0 for europium because of its stable shell. And of course, this is a very small deviation, not much different from this range. Okay. Now their reactions are pretty much what you would expect with a normal atom. It burns in O2 to give Ln2O3. With acids, it liberates H2. With halogens, it gives LnX3. With water, it gives Ln hydroxide. With carbon, it gives LnC2. With nitrogen, it gives Ln. With sulfur, it gives Ln2S3. Now look at most of them. This one, this one, this one, this one, this one, and maybe even this one. They are all showing plus 3 oxidation state, which again illustrates their stability in the third oxidation state. Okay, remember this one where they had to form a compound which is not in the plus 3 state, but also look at the reaction conditions. What conditions you had to use to force the lanthanoid to form this compound? Okay, and let's look at the NCERT paragraph. Lanthanoids are used for production of alloys, for plates and pipes. Now, misc metal, they have asked this before. Misc metal is made of a lanthanoid metal with 95% composition along with 5% iron and traces of sulfur, carbon, calcium, and aluminium. This you have to remember. Use something like escakal, school. I don't know. Just make something yourself, man. Make S-kakal and lanthanoid along with iron. This makes misc metal. Misc metal is used in magnesium based alloys to produce bullets for, like, guns. And some lanthanoids are used as catalysts in petroleum cracking. Like, you turn crude oil into petrol. So for that, a lot of lanthanoids, they are used as catalysts, and some individual oxides, they are used as phosphors in television screens and similar fluorescing surfaces. Just remember these words. Even I don't know what the hell do they mean. Just remember phosphors for TV screens and fluorescing surfaces. Now that was it about lanthanoids. Congratulations, pat yourself on the back because you have finished the biggest part of this chapter. Now, I don't want to teach you this, but just because it is in the NCERT, I am forced. And hence, let's learn about actinoids. Now, remember that trick or rather that way I told you to remember the configurations of lanthanoids? A similar trick exists here. Let's discuss it. And these are the basic configurations. Some general points are the 5F shell, 6G shell, and 7S have similar energy. And the actinoids, they are radioactive and their half-life decreases left to right. This is not a very general trend, but the NCERT says that the later elements are harder to isolate and hence we haven't been able to study their chemistry. Like, see, we don't know the sizes of their ions. Okay. So the earlier ones, their half-life is slightly longer, ranging from like 3 minutes to something like 20 hours, I guess. Their half-life is somewhat okay, but the bottom ones, they don't allow themselves to be studied. Now the 5F shell is more reactive than the 4F shell because they are not that much buried deep inside the atom. Okay, remember this as a fact, they can ask. And actinoid contraction is greater than lanthanoid contraction because the 5F shells are even more bad at shielding than the 4F shells. Keep that in mind. Okay. Now the general configuration is their configuration of radon with 7s2. So this makes a total of 88 electrons. Like for that lanthanoid, we had the value of this constant to be 56, but for actinoids, this is 88 thanks to radon plus the two 7s2 electrons. You can see there is no deviation observed. There is always two 7s electrons, and that's good. And of course, there is the rest of the electrons go in the 6d shell and the 5f shell. The value of x, which means that in the d subshell, if z belongs to 91, 92, 93, 96, or 103, and this is actinium, then the 6d shell is going to have one electron, and only for thorium it is going to have two electrons and none in the f shell, but still thorium is regarded as an f block element. And also remember this as an exception to the general configuration of f block elements, and everywhere else it is going to be 0. How do I remember this list? Well, actinium is not a actinoid, so rest of them, just remember if the ones digit is a factor of 6, okay, except for 102, all of them are going to show your 6d shell having one electron. Okay, this was the general configuration, and let's read the NCERT text. They in general show the plus 3 state again, and in the first half of the series, they can exhibit higher oxidation states like we show here, and maximum oxidation state, it increases from plus 4 in thorium to plus 5, plus 6, and plus 7 in the following elements, and then it decreases like a staircase again. Actinoids resemble the lanthanoids a lot, but here they resemble like they have more compounds in plus 3 state than the plus 4 state, which tells you again the stability of the plus 3 state. But still, the plus 3 state also tends to hydrolyze, which means it is viable to hydrolysis and it can still give a different product with a different oxidation state, and hence the reactions of actinoids, they are unpredictable. In fact, it is very obvious. I told you we haven't been able to study them properly, as properly as the lanthanoids, because they have radioactivity and hence they are unpredictable. Now let's look at their chemical properties. Again, they are silvery in appearance and they display a variety of structures. Why do they have structural variability? This can come in assertion reason. This is because of their metallic radii, which is far greater than the differences, irregularities in metallic radii, which are far greater than that in lanthanoids. Like we stated here that actinoid contraction is greater than lanthanoid one. So this irregularity leads to a lot of different crystal lattices in which actinoids can exist, and hence their structural variety is greater than that observed in the lanthanoids. Now, of course, they are radioactive, so they are unstable, and hence they are very highly reactive, especially when they are divided. Now, if we add boiling water on them, it gives a mixture of oxide and hydride. Like this is your actinoid. You add your water, boiling water, it gives a hydride, ACH3, and it gives oxide, AC2O3. Okay, and this is a mixture of oxide and hydride which is given by adding boiling water thanks to their high reactivity. And if you combine them with non-metals, this reaction takes place at moderate temperatures. Okay, hydrochloric acid attacks all of them, but they are not affected by nitric acid because of formation of protective oxide, and your bases or alkalis have no action. Okay, this might seem like an unimportant point because I cut it off a bit accidentally, but I'll just underline it. Okay, for the note readers. Now for the this paragraph, read it slowly. Okay, and these are the uses of D block elements. I cannot make you memorize this. Don't expect me to make a trick for this. What trick do you want me to make? Beta, remember this trick. Silver yoga coins are copper nickel alloy. Man, how do I tell you that cupro nickel is used to make coins of United Kingdom? Just read this one, take a screenshot, read this, and this is not that important. But one time they asked the question about this line: photographic industry relies on light sensitive properties of AGBR. Okay, and this is not just F block. This is usage of D and F block elements. So this is somewhat important, although not as important as the earlier questions. So just read this once, and another paragraph. Read this also once. Okay. This is a very important paragraph in the NCERT, which I guess you can explain yourself better than I can explain you. The only point that I want to tell you that actinoids, they have ionization enthalpies, but we haven't been able to study them really well. But they are lower than that of the early lanthanoids thanks to the poor shell of the 5f electrons. They penetrate less into the inner core of the electrons. And one more important point I can say that if we compare actinoids to lanthanoids with respect to characteristics, their similar behavior is not evident until the second half of the actinoid series. But the first half, अब go away Instagram, the first half can also resemble the lanthanoids in properties which do not entail change in oxidation state. The lanthanoid and actinoid contraction have extended effects on the sizes and therefore properties of elements succeeding them in respective periods. This is basically the zirconium and hafnium thing we studied earlier. Like radius of 5D series is similar to that of 4D series. And lanthanoid contraction is more important because chemistry of actinoids is much less known. Okay, this you remember. Read this part and users take a screenshot and read this. I am providing the notes, and that was the entirety of F block elements in one shot for your JEE Mains or NEET. And I've covered the entire NCERT, even attached screenshots where it felt necessary. And this was the last video from me, possibly before the 28th of January, and hopefully I have helped you save your inorganic chemistry, especially block and salt analysis. And this is farewell from me. But before we go, I want to tell you I am very proud of you if you have come till this point. And just that you are watching this lecture means that you are trying to save your state. And never let that warrior within you collapse. You are doing amazing. You have studied well, and you are going to absolutely demolish what was the word? Demolish, annihilate, obliterate, violate, cause massive mass destruction to the JEE mains or your NEET examination, and you are doing fabulous. Okay, keep doing well, keep slaying, and keep sending love. I will be back after mains, after which we will expand into physical chemistry and organic chemistry. Thank you and have a nice day and study well. Goodbye.